Hey everyone, and welcome to this explainer. I am absolutely pumped you're here today because we're about to explore one of the most epic, unseen battles happening right above our heads. Literally every single day, there's a silent war being waged between the raw power of electricity and the relentless forces of nature. We completely rely on this constant, uninterrupted flow of electricity to power our lives, right? But that power has to come from the outside grid directly into our homes, all while braving the elements. So today we're breaking down exactly how that crucial connection is defended.
Picture this for a second. We've all seen those heavy overhead power lines connecting the utility pole to the side of a house. Now imagine a massive storm rolls in. We're talking a torrential downpour with actual sheets of water hammering the side of your building. We all know that water and high-voltage electricity are just a catastrophic, absolutely terrifying combination. So why doesn't that mix of driving rain and raw power instantly short out your home's entire electrical supply? How is that connection actually structurally sound enough to survive the storm?
Okay, let's dive into this. The answer to that survival is completely by design. And that design is dictated by the 2023 National Electrical Code, specifically Section 230.54. Now, this code isn't just some boring list of rules, it's our ultimate architectural playbook for building a weatherproof fortress. It lays out the exact physical geometry and the mechanical armor you absolutely need to keep water out of your electrical equipment.
To understand this playbook, we're going to take a bit of a spatial journey. First, we'll look at electricity's enemy, water. Second, service heads and goosenecks. Third, above the attachment point. Fourth, separating the conductors. Fifth, the power of drip loops. And finally, the ultimate weatherproofing goal.
All right, kicking things off with Section 1, electricity's enemy, water.
In the world of electrical engineering, water is quite literally an opportunistic invader. It's relentless. It follows gravity, it clings to the surface tension of cables, and it actively seeks out the path of least resistance right into your home's service equipment. And if water actually manages to infiltrate the service raceway or the electrical boxes, well, the consequences are severe. You get corrosion, you get electrical shorts, and you literally get sparks flying. The entire defense system we're about to look at is completely based around outsmarting this opportunistic enemy.
Moving right along to Section 2, service heads and goosenecks.
So your primary shield against the rain is called a service head. According to NEC 230.54a and b, whenever you've got a service raceway or service entrance cables connecting to overhead service conductors, they must be equipped with one of these. You can think of the service head as a heavy-duty helmet. It sits right at the point of connection, physically capping off the top of the pipe or cable assembly, and most importantly, the code mandates that this head must be specifically listed for use in wet locations. It is quite literally designed to take a beating from the rain.
Now, what's really interesting about this is that the code actually offers a clever physical alternative to the standard service head, specifically for Type SE, or service entrance cable. Instead of attaching a separate helmet, the code allows the cable itself to be formed into a U-shape, what they call a gooseneck. But you can't just bend it and call it a day. To meet the standard, that gooseneck must be heavily taped with a self-sealing, weather-resistant thermoplastic. By bending the wire into an upside-down U and sealing it up, you create this natural, impenetrable barrier against ascending water.
Which brings us to Section 3, above the attachment point. Gravity is actually our best friend here. The code's ideal rule, found in 230.54c, is that these service heads and goosenecks must be located above the point where the overhead conductors actually attach to the building. Makes sense, right? If the opening where the wires come out is higher than the line running down to the street, water naturally wants to flow away from the house, not into it. But, well, architecture isn't always perfect. If it's completely impracticable to locate the head above the attachment point, maybe because of a weird roofline or structure issues, the code provides a practical exception. You're permitted to place it no further than 24 inches, or 600 millimeters, away from that attachment point. It's a compromise for sure, but one with strict limits to maintain safety.
All right, dropping down to Section 4, separating the conductors.
Let's look at the conductors themselves and see how they build our defense layer by layer. First up, under 230.54d, service entrance cables can't just be flapping around in the wind. They must be held securely in place. Movement causes wear, and wear basically just opens the front door for our enemy, water. Furthermore, under 230.54e, as the conductors exit that protective service head we just talked about, they have to be separated. Conductors of different electrical potential must be brought out through separately bushed openings. We absolutely do not want high-voltage lines rubbing against each other in a wet environment. By forcing them through their own smooth, separate, and insulated holes, we eliminate the risk of a dangerous short circuit. Actually, the only exception here is if you're using a jacketed multi-conductor cable without any splices, because that heavy outer jacket already gives you that necessary isolation.
Moving down the line to Section 5, the power of drip loops.
And this brilliantly illustrates how the code forces water to defeat itself. Under 230.54F, you have to form what are called drip loops on the individual conductors. Essentially, the wires are intentionally allowed to sag down into a loop before they travel upward into the service head. But here's the real magic of it. The actual splice, where the house's service entrance conductors meet the utility's overhead conductors, must happen either below the level of the service head or below the level where the cable sheath terminates. Why do that? Because water travels along the outside of the wire. As water runs down the overhead line toward your house, it hits that downward loop. Gravity takes over, and the water collects at the very bottom of the U-shape, where it physically has nowhere else to go but to drip harmlessly down to the ground. It completely prevents moisture from traveling upward into your sensitive equipment.
Finally, Section 6, the ultimate weatherproofing goal.
When you combine the wet-listed service heads, the thermoplastic taped goosenecks, the precise elevation rules, the securely separated conductors, and those gravity-defying drip loops, it all culminates in this singular, definitive mandate from NEC 2023 230.54G. The entire setup must, and I'm quoting here, arrange so that water will not enter service raceway or equipment. This is the ultimate golden rule. It's the exact standard by which all the mechanical steps we've learned today are judged. If water gets in, the system fails. Everything we've discussed is just a carefully engineered layer of defense designed to fulfill that one absolutely crucial sentence.
So, we've broken down the playbook. We've seen exactly how gravity, geometry, and specialized hardware all come together to protect the grid right where it meets your roofline. But, knowledge is only powerful when you apply it. So, I want to leave you with a bit of a challenge. Next time the clouds roll in and it starts to pour, I want you to step out onto your porch, look up at your home's overhead power connection, and really appreciate the unseen engineering keeping you safe. Can you spot the service head? Can you see the drip loops forcing the water down? Understanding these everyday marvels is really what makes our built environment so incredibly fascinating. Thanks so much for learning with me today, and stay curious.